Hello, everyone, and welcome to another wonderful day of chemistry. So, last time we managed to finish up our description of phase transitions for pure substances. So, today we're going to be moving into talking about mixtures. So, now we don't have to deal with only a single component at a time. Now, eventually, we're going to spend a lot of this chapter looking at phase transitions of mixtures, which is going to give us a lot of very cool information that can help us build up to reactive systems. But before we do that, we first really need to kind of define our mixtures and what we're going to use as our key properties. And that's going to be a major focus of both today and the next lecture. So, big thing is we're going to start by looking at a system with more than one component. Easiest place to start is a two-component system, and then we can kind of extrapolate what things look like from there. So, a good place to start is trying to figure out what are variances. How many variables do I need to have to define my system? So, we can do that by looking at my variance equation. So, it's going to be given by our components minus phases plus 2. So that means that if I go from a one component system to a two component, that means every single one of our descriptions needs an extra additional piece of information. That means we need three pieces of information to describe a pure phase, and I'm going to need two to describe a phase transition. So we need an extra variable to describe the system. So let's say I'm looking at a mixture of oxygen and nitrogen. So a simple model of the atmosphere. Well, this gives me 3 degrees of freedom. So we have two of our classic degrees. We've got pressure and temperature, but we need a third state variable to define our system. So we need to try and figure out what's going to be our best variable to choose from. So what do we need to describe this? So biggest thing is we want a size intensive property. So we don't want a size extensive property because then it won't scale up to a more uniform description and more importantly, a translatable description of size systems. We also want it to be able to describe each of the components separately. So I can define one component, then define the other. A unit of concentration is going to be perfect because concentration gives me a size intensive. It's a ratio of two size extensive properties. And we can also use a unit of concentration to define one component, and then based on our variance means that the other component will be perfectly defined. Now we need to choose a unit of concentration. So if I'm looking at a gas, the easy choice here is going to be partial pressure. We already have it. It works fairly well for mixtures. There's only a slight problem. It only defines gases. So we want something a little bit more general. But if we start with partial pressure, this gives us a big clue because we know that we can convert partial pressure to mole fraction. And mole fraction is going to be very good because mole fraction is going to give us a ratio of the component we care about versus the total moles. And remember, for example, if I'm looking at a gas, if I know the pressure and temperature, I know the molar volume, which means I already have a good piece of information to get that total moles. Not to mention, we can also use the fact that in mole fraction, all of our mole fractions have to sum up to equal 1. So if I have a two-component system, if I know one component, I also know the other component. If I have a three-component system, then I'm going to need two mole fractions to perfectly define the system, but I also need an extra variance. So this works very well. It's nice and universal. It's got a very good grounding in thermodynamics, as we're going to see. The problem is it's very tricky to work with because we often measure things like volumes or masses. We don't tend to measure the moles of things. So I need to try and find a way that I can easily calculate mole fractions, preferentially from a different property, or a different property I can easily calculate from mole fractions. And unfortunately, the classic chemist's favorite choice here, molarity, doesn't quite work. But molality does. So as long as I've got a very dilute system where there's a clear minority component, so that's going to be my solute, and a clear majority compound, which is going to be my solvent. And again, worth noting, this still works for gases. Turns out molality is a pretty good choice. So molality is going to define where we're looking at the molality, which we're going to designate as B. My apologies. We already have too many M's. So we're going to look at the molality of the solute. So thus the uppercase B. A is going to tend to designate the solvent. B will designate the solute. So we have the molality of the solute is going to be defined by the moles of solute over the mass of solvent. And this gives us a ratio of solute to solvent, which is going to be fairly useful. But most importantly, we can actually calculate this from mole fraction, and we can show this through a couple of steps. So if I have it defined as moles of solute to moles of to mass of solvent, well, I can define that mass of solvent based on the moles of solvent times the molecular weight. Well, it turns out that I can also define the moles of solute or solvent based on the respective mole fraction times the total number of moles. So the moles of solute are just going to be mole fraction of solute times total moles. And I can do the moles of solvent based on the mole fraction of solvent, which is just 1 minus the mole fraction of solute because they add up to 1 for a two-component system times total moles. Now, when I do this, now here we get pretty lucky because notice the total moles cancel out. So thus I'm left with a simpler expression of the ratio of mole fraction of the solute over 1 minus the mole fraction of the solute times the molecular weight of the solvent. So notice our molar properties are still in terms of solute, but our mass variable, molecular weight, is in terms of solvent. And this can kind of confuse people, so keep an eye out for it. However, this is also very nice because if I have a way to go from mole fraction to molality, that means the reverse is true. And I can figure out the mole fraction based on the molality of the solute and the molecular weight of the solvent. So again, this lets me convert both of these fairly nice back and forth. Now, one of the big questions is kind of why does this work? And we can do this by looking at my mole fraction calculation. Notice that it's given in terms of, again, this molarity of a molecular molality of the solute times the molecular weight of the solvent. Now, we can get some big insight by trying to figure out what this actually means. So if we do this, we can take a look at the units. So the molality is moles of solute over mass of solvent. Well, the molecular weight is going to give me grams of solvent over moles of solvent. So when we do this, we can again note that we have some nice cancellation. So I can cancel out kind of the grams of A. Notice I'm still left with this kilo, so I have a factor of about 1,000 that I have to deal with. But really what I get is a ratio of moles of solvent, solute to moles of solvent. And that's really what I get from this idea, is that's what these molality to a large extent really gives me, is it tells me a lot about a ratio of the moles of solute to solvent. We just have to scale it by 1,000 to take care of the units, but that's really what we have in this ratio. And that's pretty much what I get with molality. I just unit transformed it into mass. So that's the reason it's fairly easy to convert in between molality and mole fraction, is both of them are giving me these ratios of moles. And so it's going to be a fairly useful thing for us to use. And so these are going to be our classic two descriptions of concentration we're going to use the most throughout this chapter. We're going to use a lot of mole fraction. We're going to use a fair bit of molality. There's another one that is worth acknowledging, though, and it's a little bit odd. And that is going to be something called the partial molar volume. And unfortunately, it's defined with a lot of calculus. So the idea of partial molar volume is it's going to be the change in volume as I add a certain amount of moles of the component of interest, so J. So if I add, say, a mole of solute, how much will I change the volume, keeping pressure, temperature, and here's the odd one, this N star is going to be the moles of all other components. So if I keep those constant, how much will I change the volume? And normally we'll think of this idea as I increase the amount of substance, I should increase the volume by some significant amount. But it is worth noting that in some regimes, we can actually find that as I increase the amount of substance, I will decrease the volume. And a classic case of this is actually going to be adding salt to water. because that salt, being very ionic, can pull those water molecules in closer than they normally would be. And some salts at certain concentrations can actually shrink the volume of the substance, leading to a negative molar volume. And this is a little bit of an odd idea that we find. Now we can also look at these partial molar volumes by looking at the simple idea of a two-component system. So if I have a two-component system, so the change in volume should be given by this partial molar volume times how much of A I'm adding versus how much of B I'm adding times its molar volume. So if I increase B and molar volume is positive, I should see an increase in the volume. If it's negative, I should see a decrease in the volume, and we can just add these two components together. Now, it means I can get my total change in volume simply by integrating both of these independently. Now, we're going to assume that the molar volume has no mole dependence, so it should come out as a constant. And so we should have a simple integration, meaning that I can get the actual molar volume of a system, or I should get the total volume as simply by adding the molar volume of A times the moles of A plus the molar volume of B times the moles of B. Now, again, one of the things here, and again, we're doing this by assuming the molar volume doesn't change with moles, which is a little bit of a simplification. But in practice, partial molar volume is a good metric of how much volume 1 mole of a species occupies. So if I know how much mole volume each component occupies, I should get the total volume of the system. Now, again, oddities can happen if as I add a solute, it shrinks the volume of a solvent. And we do actually have some cases of this. Whereas, for example, if I have a mixture of water and I start adding ethanol, as I add a little bit of ethanol, this can actually have a negative molar volume. Well, it's going to, as the ethanol will be decreasing its volume, but this causes the water to occupy more volume in compensation. So the idea here is the ethanol will come together and go smaller while the water expands to compensate. But in general, what we tend to see is these two behaviors will um, tend to reflect each other. As one goes down, the other goes up. Now we can really examine this more next time once we learn a little bit more of how we can describe these mixtures in terms of chemical potential. It worked for phase transitions. It's going to work even better for mixtures. So next time we're going to really dive into chemical potential for mixtures. And until then, take care.